Aloha, Ohana. I was asked to make this recording, and I'm more than happy to. This recording will show let's see, put this right here, to show the how to determine how many units we have in process. There was near the end, there was one problem at the very, very end of class that we didn't quite get to. We got to the second to the last one, which is exactly the same thing with a different data set. This one has a few things that are slightly different. We had, I'll pull this up onto our screen. Create a control chart for S0328 fishery real earnings to data normal using a z-score of 1 or sigma 1. What percentage of years were out of control or out of specification? How do we interpret this? Would you consider this a stable process? So let's answer those questions. If we go to our homepage, there we have this thing right here this is the module we're in. If I click on this, it'll bring me to number 7. And what I'm looking for are the data, which is right here. And then we also want the Anderson-Darling workbook. I think I put the link to whoever it is that created. I really like it. It makes it easy it already has all the stuff we need for that. So you click on that, download the data. And once you have that, it will look like, here's the data. Okay, the Anderson thing, we're looking at real earnings. And so I'm going to copy these real earnings into here, paste values. And what I want to do, I copied it here. If there's any values below, delete those. This particular workbook only allows you to take 200 values, 200 observations, which is at least okay for most projects. A few things I want to look at is a p-value. That's probably the easiest one to look at. If you have 5% or greater, that means you can assume normality. The other thing is you look at the Anderson-Darling value, the AD. This one is about 0.6. If you take the absolute value of that as 2 or less, then you can assume normality. You can also look at this graph right here, and that looks pretty good. So I think we're okay to proceed. We have good data, at least good enough for what we're trying to do. And I'm done with the Anderson-Darling workbook. I'm going to come over here to real earnings. So is the data normal? Yes. Using a sigma of 1, a z-score of 1, what percentage of years were out of specification or out of control, whatever you want to call it? We'll figure that out. First thing I'm going to do is calculate mu, or average. I'll let that equals average. Let's see, we're looking at C. I'll use a formula for that, and I'm going to format this. Don't have to format it, but it looks a lot nicer. Well, if I can, it'll let me. Okay, let's do it this way. Currency. So there's the average. Let's look at the lower specification value and the upper specification value. Those things will guide us to what we need. I'm just going to put that in here. Not that I want those values. The lower specification value is the average, or I guess I can do that, equals average. I could just say E, let's see, average minus the standard deviation. The upper specification, we're looking at one standard deviation. If on so for the upper specification, we replace that negative sign with a plus sign. If we're looking at 2 standard deviations, right here, I would want to type in a 2 times the standard deviation, or however many sigmas we're going out. So I'm going to take those values, copy them all the way down. What I can do now, I'm going to graph this. I can use this to visually interpret what I'm doing. I think it'll make everything else make a little more sense. insert, let's make this a line graph. These are the real earnings. Real means adjusted for inflation. Remember when you were a kid, what a candy bar cost? Cost a bit more now. That's because prices adjusted for it and has changed for inflation. Okay, now that I've got the data, I'm going to add the average values. Lower, the average is interesting. What's really important though are the lower specification value, the upper specification value. In a lot of statistics textbooks, when you open that up, it will say something along the lines of upper bound or lower bound. That's what I'm used to calling them. But in Six Sigma, at this point during the measure stage, you call it lower specification value, upper specification value. Want to be technically correct. When you're looking at controlling your process, you could call it your lower control value or your upper control value. Although in some of the literature that I've read, they'll just call it control instead of specification. I guess as long as you know what you're talking about, that's the important thing. And when I'm looking at this, some of these are out of control or out of specification. Anything that's above the upper specification value, these things are out of specification. These values over here are below specification. So we're outside of the specification value. That's like if you're driving down Cam Highway, you want to make sure you're within the lines. If you cross over to the left, well, you might hit oncoming traffic. Cross over to the right, you could go off the road, which or hit a pedestrian. All sorts of problems can happen. So you want to stay within bounds. And because we're looking at one, well, I mean, we want to stay within the bounds, the correct amount of time. We have a fairly narrow bandwidth. We're looking at one standard deviation. So you want to stay at least 68.2% of the time within there. Now we wrote these formulas to give us the upper and lower specification. I'm going to write one more to determine if these values they have right here that we're looking at, this line, the real earnings are within the specification values. And I'll do that with a formula called if and. So if this value, let's see what's going on here. Okay, equals if real earnings is greater than or equal to the lower specification value and the real earnings is less than or equal to the upper specification value. Really what that means is, are we within the two bounds? If we're within the bounds, then we are good. And we'll say it's good by giving a value of 1, or we'll give it a value of 0 if it's not good. And let's make sure it's behaving like we thought we would. Those first two values, 62,000, that is less than the lower specification value. 110, less than. Okay, so yeah, we want those to be zeros, big fat zeros. About 127. 127 is bigger than 120, less than 370. So that should be a 1. Okay, looks like it's behaving like I thought it would. Now to see what proportion of these are within specification, I'll do equals, I'll sum up all the ones, divide it by the count. Let's see, H2 to H49. And that gives me 62.5%. I'm going to turn that into percent. So 62.5% are within specification, which means it's not a stable process. How do we interpret it? We're out of specification. We're less than 68.5%. So that means it's not stable or things. You might have some sort of thing that's going on there that's not being accounted for. That's something's causing a change in here. Okay, great. If we were to change these, make these within 2 standard deviations, look at that. These ones, now we're at 97.9%. We need at least 95%. So if you make it 2 standard deviations, give it a wider bandwidth, I guess you're okay. But anyways, it's more ethical. You want to establish what your boundaries are before you start taking measurements. And So anyway, going back to answer this question, is it within one standard deviation? Yes, because, oh, actually, no, we're not, because we're at 62.5% when we need to be at least 68%. Anyway, I hope this video was useful, and let me know if you have, shoot me an email or come by office hours if you have any questions about this email, about this process that we just did.